Okay, let's talk about sequences. This is a new topic, and it's a word that probably has some meaning to you, but let's just give the mathematical definition that a sequence, as you might guess, is just a list of numbers. Um, but I will say that, especially in calculus, it's often considered to be an infinite list. And so any list, we just start listing numbers in some, with some pattern. The idea is to hopefully hope that there's some pattern in the numbers. Otherwise, why do we care about a sequence of random numbers? Let me just give some examples, and then I'll start to tell you about the notation and about some subtleties that start to arise. So, we could just do the counting numbers, right? We could just start listing 1, 2, 3, 4, 5, 6, 7, and keep going. So these are the positive integers, counting numbers, whole numbers, however you want to describe them. We could list the perfect squares if we wanted. 1, 4, 9, 16, 25, 36, 49, 64, and so on. How many can you name? Those are the squares. We could do something like the powers of 2. 1, 2, 4, 8, 16, 32, 64, 128, and so on. There's no reason they have to be whole numbers. We could do, 1, a half, a third, a quarter, a fifth, a sixth, a seventh, and so on. This actually has a name. It's called the harmonic sequence. Just 1 over the integers. And let me talk about a little bit of notation, because how do we write down mathematically a sequence, right? So the notation is that we would write something like a sub n for the nth term of a sequence. This is just standard. I mean, you could say b sub n or x sub n, or you could use different letters, but and just as an example, right, if we try to start labeling the very first one, right, like if we go back to example 1 for a second, a sub 1, that's the first term, is 1, a sub 2 is 2, a sub 3 is 3, and so on. And it's pretty clear that a sub n is n, right? The nth term is just n. So we could write this, a sub n is n. We do want to tell where it starts, n equals 1, so on. So that's one way to write down the sequence, like to give just a form of the sequence. Another way you'll see it written is kind of in set notation, where we just say it's the set n starting from n equals 1 to infinity. And that's supposed to somehow indicate, maybe this is a little bit more to indicate in set notation, that you could start listing. It's supposed to be a 5. Right, so that's just a shorthand for that. So you'll see either of these sort of things as a way to sort of write down a sequence, right? Because there's a dot, dot, dot at the end. You have 1, 2, 3, 4, 5, 6, 7, dot, dot, dot. And sort of there's a promise in the dot, dot, dot that you're going to keep going. The next one's going to be 8, 9, 10, and so on. But, if you don't have enough terms to really tell what the pattern is, then you want to sort of give a general formula that will sort of say, okay, this says that the 1,000th term is 1,000. And so it gives a more general list. So for the second one, the squares, right? Say you didn't, recognize they were the squares. You could also do something like this. You could start making a chart, like a table. I can be a little fancier and make these straight lines. So here's a table. Probably a fast way to do this. um, a little fussy. Okay, so you start counting from 1, and you see 1, 4, 9, 16, 25. Did I get the right? Okay, I was afraid I skipped one on my list up there. And etc., right? And you can kind of guess that in general, if I put an n here, then you know it's going to be n squared. And it sort of matches. You can sort of check for any specific, if I have 5 here, then, oh, I get 5 squared here. Right? And so again, we could write that as a sub n equals n squared, starting from n equals 1, or the set n squared n equals 1 to infinity. Now the third one is where this becomes a tiny bit more interesting. Right, I have the powers of 2 starting 1, 2, 4, 8, 16, 32, and so on. So let me do this table again. I think I'm not going to be as, well, maybe I'll make this one horizontal line straight, and then the rest I'll just not be as fussy. It takes too long to sit there and let them straighten themselves out. Okay, so we do 1, 2, 3, 4, 5, 6, probably enough. 1, 2, looks kind of funny, 4, 8, 16, 32. I'll go ahead and go 7 and 8, 64 and 128. Now, what's the formula then? Well, maybe you start writing these down and you say, okay, this one here is 2 to the first. This is 2 squared. This is 2 cubed. This is 2 to the fourth, 2 to the fifth, 2 to the sixth, 2 to the seventh. 1 is actually 2 to the 0. And if you now start matching up the, oh, by the way, this is called, there's a word for this. This subscript here is called the index. And so these are all indices. So like the point I want to say is if you look at 4 here, when you it's almost like a function where you're inputting whole numbers and you're outputting some numbers. And so 4 gives you 3, 5 gives you 4, 6 gives you 5, 7 gives you 6, and etc. And you can probably guess, you can sort of see the pattern from this, that the nth term is not 2 to the n. You have to be a little careful. It's 2 to the n minus 1. Again, starting from n equals 1. Or, like I said, we could write that as just 2 to the n minus 1, going from 1 to infinity. But, it's a little annoying because the exponent didn't match the index. So we could really make the exponent match the index if instead, if I have the same list, but I make my n's that correspond now, I'm just going to demarcate these boxes. If that was actually n equals 0, 1, 2, 3, 4, 5, etc., then that would really match, right? The 0 here would match the 0 there. The 1 here would match the 1 there. So the only thing we do is we just have to start counting from 0. That's the only difference. And so it's the exact same. I claim this is just another answer to, like, if you want to list the sequence, you could say, so you could give it this way, or you could say a sub n is 2 to the n, but we start counting from 0. And that's the big thing there, is we just start counting at a different point. And that's often very useful because sometimes it's just a more natural formula. Like I like 2 to the n as a formula better than 2 to the n minus 1, just because it sort of fits more naturally with the nth term being 2 to the n, right? So again, you could write this as 2 to the n, but now at the bottom, instead of saying n equals 0, n equals 1, you say n equals 0 to infinity. And so, this is the starting index. this 0 here is this where we start. It's the starting index. I don't know if that's such an official term, but hopefully you understand what I'm getting at. All right, and because and just to keep going with more examples, you could sort of see like how this could come into effect very quickly, right? Like say I want to do something like, here's a sequence, 1/6, 1/7, 1/8, 1/9, 1/10, 1/11. Right, you could go through the rigmarole of figuring out that when n is 1, a sub n is 1/6. When n is 2, a sub n is 1/7. When n is 3, a sub n is 1/8. And so on, and you could eventually see, okay, well, in that case, a sub n is, I'm just adding 5 to the denominator. Starting at n equals 1. But it makes so much more sense. It's like you just want to start counting. It's just easier to start counting at 6. So I would more naturally say, let's just start counting this at 6. So really, I would prefer the answer a sub n is 1 over n, just starting at n equals 6. To me, this is a slightly better answer for this example. Or you could, again, you could also write this as set notation, 1 over n equals 6 to infinity. Okay. You can get more and more sort of clever about this. You could say, let me just give a couple more examples and then I'll wrap up. You could say, here's a sequence. You can make up any sequence of any list of numbers and call it a sequence. 3 pi, 2 pi, pi, 0, negative pi, negative 2 pi, negative 3 pi, negative 4 pi, and so on. So I'm just going down by pi each time. Well, in this case, if we start labeling our indices, if we start counting at 1 or 0 or I don't know, but what do we want to start counting at? Do we want to start counting at 1? The third term is pi, the fourth term is 0. You could figure out, there is a formula there that you could figure out. It wouldn't be that fun. But I don't really like that. So let's just start at, well, we could start at 3, but then we're going up. The problem is you always have to count up. The index should always be incrementing by 1. Like if you start at 6, the next one should be 7. So I'll tell you just maybe a slick way to think about this. What if we made this, we eventually want to get negatives. So what if we start this at negative 3, negative 2, negative 1, 0, 1, 2, 3, 4, and so on. If you start, so I'm basically making that table of, n and a sub n. I just don't know. I'm just being lazy. I'm not rewriting the whole thing. So you could then say that a sub n is negative n pi, starting at n equals negative 3. There's no reason you can't start wherever, right? So again, or maybe it's nicer to write negative n pi starting at from n equals negative 3 to infinity. And just to check, a sub 5 is negative 5 pi. And so that's somewhere down the list. It's going the right direction, right? A sub 5 is negative 5 pi, a sub 6 is negative 6 pi, and so on. And so you're counting, and that seems to work. Okay. 2 more quick examples. Here's an example that's kind of famous. What if I just do 1, minus 1, 1, minus 1, 1, minus 1, 1, minus 1, and so on? It turns out the nice way to get this is to think about the fact that when you multiply minus 1s, right? If you multiply minus 1 by itself, it keeps going back and forth between 1 and negative 1. So in fact, you can say a sub n is minus 1 to the n. Then you just have to figure out where to start. We want to start with a positive number. So I can't start with n equals 1, right? That doesn't work. You can start with n equals 2 if you like, but people tend to start with n equals 0. And so that's just sort of a natural, if you start with 1. If you start with negative 1, you could use negative 1 to the n. But if you start with positive 1, I'm sorry, if the formula is negative 1 to the n either way. If you start with -1, you can start at n equals 1. But if you start at 1, you should start at n equals 0. So like I said, we could write this as the sequence -1 to the n, starting from n equals 0 and going to infinity. Okay. One last famous example that's just students, it'll come up a lot. What if I wanted to list the odd numbers? Because we're sort of stuck with, incrementing the index by 1. So I can't just say a sub 1 equals 1, a sub 3 equals 3, a sub 5 equals 5. So I'd have to indicate that I'm skipping every other number. But that's just really what counting the odd numbers is. So how can we get this as a formula? And I'll just sort of tell you the answer, that you could do something like the following. We'll talk about a more general version of this called arithmetic progressions, but you could just use 2n plus 1. That's a nice way to list the odd numbers. I guess if I do 2n plus 1, I'm starting at n equals 0. You could also do 2n minus 1 and start at n equals 1, and so on. So it's either one of those. So this sequence, which probably I really should give as a set, you could say it equals the set 2n plus 1, n equals 0 to infinity, or it equals 2n minus 1, starting from n equals 1 to infinity. But right, if you keep plugging in the numbers, if you plug in 0, you get 1. If you plug in 1, you get, well, sorry, I'm pointing at something. If you, just look at this one. If you plug in 0 for n, you get 1. If you plug in 1, you get 3. If you plug in 2, you get 5. If you plug in 3, you get 7. And so 2n plus 1 or 2n minus 1 is a nice way to list the odd numbers. All right, that's enough examples. I will talk about some more specific things in future videos.